Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll be discussing rulers. This material is produced for Ohio University Math 3110-5110 College Geometry. The topics for this video, rulers and metric geometry, are from section 2.2. I'll be discussing the definition of ruler, diagrams illustrating the ruler equation, examples of rulers, and then I'll introduce what's called metric geometry. There's a typo here. I won't be discussing that. The corresponding reading is pages 30 to 35 of section 2.2, metric geometry, in the book Geometry, a Metric Approach with Models, 2nd edition by Millman Parker. The corresponding homework is this collection of exercises, 9 exercises from section 2.2. Quite a long list, but a lot of those are not very hard. So I have, just for our reference, some important definitions from section 2.1, the definitions of abstract geometry and incidence geometry, the procedure for finding the Cartesian line passing through two distinct points in R2, and the procedure for finding the Poincare line passing through two distinct points in the upper half plane. Remember these procedures. The procedure for finding those lines depends on whether or not the 2 points have the same x-coordinate or not. If the 2 points do have the same x-coordinate, then the Cartesian line is a vertical line that has x-coordinate that's that same x-coordinate. If we're considering those points in the Poincare plane and they have the same x-coordinate, then their line is called a type 1 line. It looks like a vertical line, but it's just in the upper half plane. If the 2 points have different x-coordinates, and we're considering them as points in the Cartesian plane, then we find the slope and the y-intercept of the line that passes between them using the usual tools for doing that. And we just build this symbol, L subscript m comma b. On the other hand, if we're considering the points as points in the upper half plane, in the Poincare plane, and they have different x-coordinates, then we describe the line that passes through them by finding the center and the radius of that semicircle that they lie on, and we write this symbol, CLR, for the type 2 line that passes through them. A distance function on a set S is a function from S cross S to the real numbers. So in other words, a function that eats as input a pair of things from S and spits out as output a real number. And a distance function has to satisfy these three requirements. And I introduced, 5 examples of distance functions. The absolute value distance function on R, denoted this way, D subscript double struck R, so that behaves this way. The distance between real numbers x and y is computed using this formula. Then I introduced 3 distance functions on R2. The Euclidean distance function with the familiar Euclidean distance formula, the Taxicab distance function with this distance formula, and the max or supremum distance function with this distance formula. And I introduced the Poincare distance function on the upper half plane. And remember that when computing the Poincare distance between 2 points, you have to determine first whether or not the 2 points have the same x-coordinates. If they do, then you compute the distance between the points using this fairly simple formula involving just the y values. On the other hand, if the 2 points have different x-coordinates, then you have to use this very messy formula to find the distance between them. And that formula involves the center and the radius of the type 2 line that passes through P and Q. So you have to first find the value of C and R, and then use them to compute this mess. Now I want to discuss rulers as a way of measuring distance in drawings. So we've introduced 3 distance functions for the Cartesian plane and a distance function for the Poincare plane. Those distance functions enable us to find the distance between points using the xy coordinates of the points. If our goal was just to be able to measure distance, then we'd be done. We have a great way to do that. But at the beginning of the current section, it was observed that there is nothing in the axioms for incidence geometry that requires that a line contain an infinite set of points. Indeed, we saw that there were a bunch of examples of finite geometries that qualified to be called incidence geometries. Well, you might think at first that we could simply add an axiom that requires that all lines have an infinite set of points. Typo here. But it's not that simple. We want the behavior of lines that's prescribed by our axioms to mimic the behavior of lines that we observe in our informal straight line drawings. One aspect of that behavior has to do with the way that we measure distance in drawings. In our drawings, we don't measure distance between 2 points by using the Euclidean distance formula. We find the distance between P and Q by putting a ruler alongside the line that contains points P and Q. We use the ruler to get numbers that correspond to the points P and Q. These numbers are called the coordinates of P and Q. And then we subtract the coordinates of P and Q to find the distance between P and Q. We'll define something analogous to this process in our incidence geometries. The thing that we'll introduce is fittingly called a ruler. Just as a ruler in a drawing is related to the distance in a drawing, the ruler in an incidence geometry will be related to the distance function, if there is one. In other words, the definition of a ruler will only apply to incidence geometries that have distance functions. So here's the definition of a ruler for a line. If I say these words, F is a ruler for line L, or these words, F is a coordinate system for line L, or these words, F is a coordinate function for line L, all those things mean the same thing. I use them in a situation where I have an incidence geometry with a set of points and a set of lines in the discussion, and when I have a distance function, D, on this set of points in the discussion, and when L is a line in my set of lines. So I only get to use these words when I have all of this stuff in the discussion. But what does it mean? What do those words, F is a ruler for line L, mean? Well, they mean this. F is a bijection from L to the set of real numbers. So it eats as input a point on line L and spits out as output a real number. And it has to satisfy, the function f has to satisfy these requirements. F has to be a bijection, and f has to agree with the distance function d in the following way. For each pair of points P and Q, not necessarily distinct, on that line, this equation has to be true. If I do this computation, find the coordinate of P, find the coordinate of Q, subtract them, take the absolute value, I have to get the same answer that I would get if I computed the distance using the distance function. This equation is called the ruler equation, and the number f of p is called the coordinate of p with respect to f. Now I want to talk a little bit about illustrating the relationship between a ruler and the distance function. Notice that given 2 points P and Q on a line, there are 2 different processes that can be used to produce a real number. The first process is this. Feed the pair of points P and Q into the distance function, the function d, to get a real number denoted d parentheses P comma Q. That's called the distance between P and Q. That process could be illustrated with this arrow diagram. The bottom half of this diagram we've seen before. It's part of the arrow diagram that tells us that d is a function with domain script p cross script p and range r. So we've seen that kind of arrow diagram in the function description for d. So that's just the arrow diagram that tells us that d is a function. But the top of the arrow diagram, this thing, tells us what actually happens to a pair of points. A pair of points, P and Q, get sent to this real number, d parentheses P comma Q. So that's process 1 for getting a real number from the pair of points P and Q. Process number 2 is a two-step process. The first step is we use L, that's the line passing through points P and Q, and we let F be that ruler for that line. We feed point P into F to get just a real number called f of P. That's the coordinate of P. And then we feed Q into the function f to get a real number f of Q. That's called the coordinate of Q. So now we have a pair of real numbers, f of P, f of Q. Now the second step is to feed that pair of real numbers into the distance function on the set of real numbers, that function d subscript double struck r. Now when I do that, I get this. The distance between those real numbers is computed that way. So that two-step process can be illustrated with a two-step arrow diagram. I take the pair of numbers, I feed each of them through f to get coordinate for each of them, and then I use the real number distance function to get the distance between those two real numbers. So the ordered pair p comma q produces this number. Now that we've identified two different processes that can be used to turn a pair of points on a line into a real number, an obvious question is this: do the two processes give us the same result? That is, for any 2 points P and Q on line L and a ruler for line L, does this number that we got from the distance function equal this number that we got from the other two-step process? Well, the fact that f is a ruler guarantees that those results will always match. That is, the result of process 1 will always equal the result of process 2. That number will always equal that number. The fact that these two processes always yield the same result can be illustrated by combining the two arrow diagrams into a single larger diagram. In order to improve readability, I'm going to bend the diagram for process number 2. The resulting diagram is this. Here's process number 1 going from here to here. Process number 2, that two-part process, is this. Part 1, step 2. In the diagram, we see that there are two different routes to get from a pair of points, that is an element of P cross P, down here to the set of real numbers. The slanting arrow, that blue arrow, is process number 1, and the two-step path that goes across on the green arrow and down on the red arrow, that's process number 2. The circled equal sign in the middle tells us that these two paths always yield the same result. In diagram jargon, we say this. We say that the diagram commutes. You say that a diagram commutes when alternate paths from some place to some other place always give the same result. We can superimpose on the diagram some additional symbols that show what happens to an actual pair of points. Remember, the first process, we take a pair of points, we feed them through the distance function, and what comes out is this real number. In the second process, the two-step process, we first feed each of those points into the coordinate function by themselves to end up with this pair of real numbers that are the coordinates of those 2 points. And then we feed that pair of numbers into the distance function for the real numbers. That is, we find the distance between those 2 real numbers, and we end up with this real number. And the point is that these 2 real numbers are always the same. Now I want to talk about metric geometry. The general symbol for a metric geometry is a script M. It's an ordered triple, P, L, and D, that satisfies the following. First of all, P and L is an incidence geometry. And then D is a distance function on the set of points, script P. So that's 2 requirements on these 3 letters. The third requirement is this. Every line in the set of lines has a ruler. This requirement is called the Ruler Postulate. If this triple satisfies all 3 of these requirements, then we say that that triple is qualified to be called a metric geometry. Here are 4 examples of metric geometries. Some of these are presented as propositions in the book. Proposition 2.2.4 says that this triple, consisting of the Cartesian plane incidence geometry along with the Euclidean distance function, that triple satisfies the ruler postulate. That is, every line has a ruler. And so therefore, that triple is qualified to be called a metric geometry. We call that the Euclidean plane, script E. Now here, I made a mistake in a previous video. I said, mistakenly, I said that the Cartesian plane is synonymous with the Euclidean plane. It's not. The Cartesian plane refers to this pair, this incidence geometry. The Euclidean plane refers to this triple. When you say Euclidean plane, you're talking about using the Euclidean distance function. That's one example of a metric geometry. Proposition 2.2.7 in the book says that this triple, which consists of the Cartesian plane again, and the Taxicab distance function, also satisfies the ruler postulate. So that is, every line has a ruler. And so therefore, this triple is qualified to be called a metric geometry. This triple is called the Taxicab plane. Use the script T to denote it, and it's that triple. So notice that the Taxicab plane is a metric geometry. The underlying incidence geometry is the Cartesian plane incidence geometry. The Euclidean plane is a metric geometry, and its underlying incidence geometry is also the Cartesian plane. So the Cartesian plane is an incidence geometry that can be used in more than one metric geometry. It's a fact that this triple, the Cartesian plane incidence geometry combined with the max distance function, also satisfies the ruler postulate. So that triple is a metric geometry, and we call that the max plane. So three different metric geometries that all have the Cartesian plane as their set of points and set of lines. In Proposition 2.2.6 in the book, the authors prove that the triple consisting of the Poincare plane incidence geometry along with the Poincare distance function satisfies the ruler postulate. So it's qualified to be called a metric geometry as well. Now we use the same symbol, the script H, for that metric geometry. So we use the script H for this incidence geometry, and we use the same script H for this metric geometry. That's confusing. I won't provide proofs that any of these four things that I've called metric geometries actually are qualified. But again, the book provides a detailed proof of Proposition 2.2.4 about the Euclidean plane, and they provide a partial proof of Proposition 2.2.7 about the Taxicab plane. Now you will be asked to finish that proof in your homework exercise, 2.2 number 12. We'll accept without proof that the max plane is qualified to be called a metric geometry. The book provides a detailed proof of Proposition 2.2.6 about the Poincare plane. So you are only responsible for this proof about the Taxicab plane, about part of it. Now, as I said, I won't discuss the proofs here, the proofs that these things really are qualified to be called metric geometries. But remember that to be called a metric geometry, you have to satisfy the ruler postulate. Every line has to have a ruler. So even though I won't discuss the proof that these things that I've presented as metric geometries are really qualified to be called metric geometries, I'll point out that part of the proofs involve producing ruler functions that work. If you want to say that something is a metric geometry, you've got to come up with, for any given line, an example of a ruler function for that line. Well, the table on the next page presents rulers that do work. So here are rulers for some of our incidence geometries. The table presents rulers for the Cartesian plane with three different distance functions. Cartesian plane with the Euclidean distance function, Cartesian plane with the Taxicab distance function, and the Cartesian plane with the max distance function. For each of those, I have to show that for each kind of line, for instance, in the Cartesian plane, For the vertical line, I have to come up with a ruler that works for vertical lines. That's that function. And I have to show that for non-vertical lines, there's a ruler that works for them. That's that function. For the Cartesian plane with the taxicab distance function, I have to show that there is a ruler that works for vertical lines. It's that function. And I have to show that there's a ruler that works for horizontal lines. That's that function. Let's skip down to talking about the Poincare plane incidence geometry with the Poincare distance formula. I have to show that there is a ruler that works for type 1 lines. Well, there's the formula for the ruler that works for type 1 lines. And I have to show that there's a ruler that works for type 2 lines. There it is. There's a typo here. This should say r squared. So again, the fact that these rulers really do work as rulers, that they satisfy the requirements of a ruler, that's part of the proof that those things that I was calling metric geometries really do work as metric geometries. So I won't discuss the proofs here, but we will use these results. We will use the fact that we have these rulers. Let's do some examples. We'll do 2 examples involving computing coordinates of given points. So example 1 is points on a type 1 line in the Poincare plane. So let A and C be these points. A is the point 1, 3, and C is the point 1, 5. Find the coordinates of A and C on the Poincare line L that passes through them, using the standard ruler for line L. Well, notice that A and C have the same x-coordinate. So that means that the Poincare line that passes through them is a type 1 line. It's the Poincare line 1L, that it's the type 1 line with x-coordinate 1. So we have to go up and find the formula for the ruler of a type 1 line. In the Poincare plane, for a type 1 line, this is the formula for the ruler. F of a comma y is going to be ln of y. So we use that formula. F of 1 comma y is ln of y. So that means f of a is ln of 3. Notice that I've done my usual. I've written down the exact answer first. The exact answer is ln of 3. And the approximate answer is 1.099. Now we compute the coordinate of C using the same ruler. Now I say use the coordinates to find the distance between A and C. What I really should have said is use the coordinates to find this quantity. So when I do that, this is what I get. So the result is this quantity is ln of 5/3, which is roughly 0.511. Question C is to use the distance function, the Poincare distance, to find the distance between A and C. Well, let's go back up and review that calculation. The Poincare distance function works this way. If 2 points have the same x-coordinate, then the distance between them is computed using this formula. So when I use that formula, I get the following. I get ln of 5/3 again. Compare the results from B and C. Is the ruler equation satisfied? Well, yeah, the result of this calculation was ln of 5/3, and that's the same as the result of this calculation. Question E is to illustrate those results. All right, well, I'll start illustrating these by labeling my points. Here's point A, 1, 3. Point C is 1, 5. Now I want to illustrate the coordinates and the difference between those coordinates. I'm going to do that using a number line. So you see the coordinate function, or the ruler function f, takes as input this green point and spits out as output that green real number that lives over here on the number line. This is the set of real numbers. That number line depicts that. This drawing on the left is the Poincare half plane. It's the upper half plane. The same ruler, the same coordinate function, takes as input this point, C, and spits out this real number. And the difference between those two real numbers is that. That's the end of that example. Let's go on. Example 2, we're going to consider points with different x-coordinates in the Euclidean plane. So let's let B be the point 1, 4, and let D be the point 8, 3. Find the coordinates of B and D on the line L that passes through them using the standard ruler for that line in the Euclidean plane. Well, notice that B and D don't have the same x-coordinate. So in order to find the coordinate function for a non-vertical line, we need to do this. We need to build that formula. F of xy equals x times square root of 1 plus m squared. So we need the slope of that line. Now with the slope, then, we can build the formula for the ruler function. So we end up with the formula that f of xy is x squared of 50 over 7. Using that, we can find the coordinate of B and the coordinate of D. Now we can compute the absolute value of the difference. So the result is the coordinate of B is this number, square root of 50 over 7. The coordinate of D is this number, 8 square root of 50 over 7. When I find the difference and take the absolute value, I get this number, square root of 50, which is approximately 7.07. Question C. Use the Euclidean distance function to find the Euclidean distance between B and D. So notice that the Euclidean distance is the same value that we got using this calculation. So the standard ruler formula for that Cartesian line using the Euclidean distance function does work. Question E is to illustrate the results from A and C. Well, here's line L. Now, how can we illustrate this? Well, as before, I'm going to draw a number line showing where this point B and this point D have their coordinates. So when I use the coordinate function, or the ruler function, f, the result is the coordinate of B is this number, and the coordinate of D is this number, and the difference between those two numbers is square root of 50. That's the end of that example. Example 3. Points with different x-coordinates in the taxicab plane. So we have the same two points, B and D, 1, 4, 8, 3. We have to find the coordinates of B and D on the line L that passes through them using the standard ruler in the taxicab plane. Well, remember, the line that passes through them is the same Cartesian line. Now let's go back up and look at the standard rulers in the taxicab plane. For the taxicab plane, we have to figure out if the line is a vertical line or a non-vertical line. Well, that Cartesian line that passes through B and D is a non-vertical line, so we need to build this formula for our standard ruler. Now we already know the value of the slope. The value of the slope was minus 1/7. So we build the standard ruler. So the formula is f of xy is x times 8/7. So using that ruler, we can find the coordinates of B and D. So the coordinate of B is 8/7, which is roughly 1.143. The coordinate of D is 64/7, which is roughly 9.143. Question B, we have to compute this difference. The result is that we get a value of 8. Question C, using the taxicab distance function, find the taxicab distance between B and D. Well, remember how the taxicab distance function works. I have to do that calculation. Well, let's see. I get the number 8. For question D, compare the results from B and C. Well, in part B, we did this computation and we got the number 8 as a result. In question D, we did this computation and we got the number 8 as a result. So the ruler equation is satisfied. Question E is to illustrate the results from A and C. Here we can see that point B is over here, point D is over here. The taxicab distance between them is 8, and that's obtained by going down 1 and over 7. And if we think about that in terms of the coordinates, if I find the coordinate of B, I get this number, 8/7, and I find the coordinate of D, I get this number, 64/7. The difference between those numbers is the number 8. We should go back up to our earlier drawings. This illustration, the difference between these coordinates was square root of 50. The Euclidean distance up here was square root of 50. And let's go back up to our earlier drawing in the Poincare plane. When we did the computation involving finding the coordinates and then finding the difference of the coordinates, we got that number over here in coordinate land. When we used the distance formula for Poincare distance, we found directly that the distance between A and C was ln of 5/3. Let's go on. Now example 4 is hard. We're going to consider points with different x-coordinates in the Poincare plane. So B is that point 1, 4. D is this point 8, 3. We're going to find the coordinates of B and D on the line L that passes through them using the standard ruler for that line in the Poincare plane. We'll notice that it's a type 2 line. So we need to find its center. We use the formula for the center of a line. So the type 2 line has center C equals 4 and radius R equals 5. Now we use the formula for the ruler. We build that, ln of x minus c plus r over y. When I find the coordinates of point B, I get the following. So we find the coordinate of B is negative ln of 2. That's the exact answer. And that's approximately negative 0.693. The coordinate of D is, ln of 3 is the exact answer, and that's approximately 1.099. Now we have to compute the absolute value of the difference. We see that the absolute value of the difference between those two coordinates is the number ln of 6, which is roughly 1.792. Question C. Use the Poincare distance function, d subscript h, to find the Poincare distance between B and D. Remember that the Poincare distance formula is this. So we have to build that. We get an answer of ln of 6, which is roughly 1.792. So question D is to compare the results of B and C. Is the Ruler equation satisfied? Well, notice in question B, we computed this difference and we got ln of 6. In question C, we computed this distance and we got the result of ln of 6. So we see that the Ruler equation is satisfied. Question E is to illustrate our results here on this diagram. Well, let's label our points B and D, and this hyperbolic distance is ln of 6. Now let's illustrate the action of the coordinate function, the ruler. So here's the set of real numbers. When I use that ruler, the point B gets sent over to its coordinate, which was minus ln of 2. And if I feed the point D through the coordinate function, what comes out is its coordinate, which is ln of 3. And if I compute the difference in those two coordinates, I get ln of 6. So the difference in the values of the coordinates is the same as the distance between the points using the distance formula. Now I want to discuss finding the point that has a given coordinate on a given line with a given ruler. So suppose we have a line in a metric geometry and it has a ruler f. Then f is a function that eats points on the line as input and spits out real numbers as output. So the inverse relation will be a relation from R to L. And furthermore, since f is known to be bijective, remember that's one of the requirements for rulers, the inverse relation f superscript minus 1 will actually be qualified to be called an inverse function. Now it's possible to find the general formula for the inverse function for each of our standard rulers. That would involve solving equations, and some of the equations are terribly messy though. So for that reason I won't discuss finding the general formula for the inverse functions for each of those rulers in these notes. The textbook also does not describe it. But I will present some examples involving finding the point that has a given coordinate on a given line with a given ruler. You do have some homework exercises of this type. In these problems, it's helpful to use the symbol lambda to denote the value of a coordinate. So example 5, finding a point with specified coordinate on lines in the Euclidean plane. Question A is find the point P on the vertical line L3 that has this coordinate, lambda equals 5 is the value of the coordinate, in the standard ruler for that line. Okay, well this is a fairly easy one. Since the line we're talking about is a vertical line, we know that the point P must be of this form, 3, y, because it's on the vertical line L3. So the x-coordinate has to be 3. And we know that the standard ruler for that line is this. F of a, y is the number y. So in other words, the value of the coordinate, the lambda, is obtained by using that formula. Now in this example, we're given the value of the coordinate is 5, and we know that the number a is 3 because the line that's in question is the vertical line, L3. And so the fact that the coordinate is 5, that is the lambda equals 5, that's giving us the value of the y-coordinate. So P has to be the point 3, 5. So that's pretty simple. Question B. Find the point P on the non-vertical line L3, -4. So that's a line that has slope 3 and y-intercept -4. Find the point on that line that has a coordinate lambda equals 5 in the standard ruler for that line, for that non-vertical line. Well, the standard ruler for the non-vertical line is this formula, f of xy equals this formula. Now when I use the value of m, our line has slope 3, that's our m, so this formula actually turns out to be this, x squared of 10. So that's a formula that takes the value of x and spits out a value of lambda as a result. That's the ruler function. Now we are given x equals 5. So that means that's the value of the lambda. That's the value of the coordinate that you get when you do that calculation. When you solve that formula, solve that equation for x, we obtain that x is 5 over square root of 10. Now, that's the x-coordinate of P. How do we get the y-coordinate? Well, P is on a non-vertical line, so that means that it's got to satisfy this line equation. Slope m is 3, and the y-intercept b is -4, so y and x have to satisfy that equation. We know the value of x, so we can use this equation to get the value of y. We do that, and we end up with this as the y-coordinate. So our point P is that x-coordinate and this y-coordinate, which is roughly these decimals. Example 6, finding a point with specified coordinate on a line in the taxicab plane. So now let's let the line be, again, the vertical line, L3, and let's look for the point P that has coordinate lambda equals 5 in the standard ruler for that line in the taxicab plane. Well, question A is the same as it was for the Euclidean plane because the ruler for vertical lines in the taxicab plane is exactly the same as the formula for the ruler for lines in the Euclidean plane. So we end up with that P has to be the point 3, 5, just as we did in the previous example. But for question B, we're going to be considering point P on the non-vertical line L3, -4 that has that coordinate in the standard ruler for the taxicab plane. Well, remember that in the taxicab plane, the ruler has this form, f of xy equals x times 1 plus absolute value of m. When I use that value of m equals 3, I put that in there, I end up with this formula that the coordinate f of xy is just 4x. So that's how you get the lambda from x. Well, in our problem, we're given the lambda. It's 5. So we know that 5, that's the lambda, has to equal 4x. When we solve that for x, we get x equals 5/4. So that's the x-coordinate of our point P. Now, how do we get the y-coordinate? Well, now we're just talking about a Cartesian line, this non-vertical line with slope 3 and y-intercept -4, and we know that y is on that line, so y has to obey that equation. So we plug in that value of x, and we obtain from that line equation this value of y. So the coordinates of P are that x-coordinate, 5/4, and that y-coordinate, -1/4. Finally, example 7, finding a point with specified coordinates on lines in the Poincare plane. So question A, find the point P on the type 1 line, 3L, that has coordinate lambda equals 5 in the standard ruler for that line in the Poincare plane. All right, well, in question A, we were dealing with a type 1 line. So that means that point P has to be of this form, 3 comma y. Whatever that x-coordinate is for that line, that's got to be x-coordinate for point P. Furthermore, we know that the standard ruler for a type 1 line in the Poincare plane is this. F of a comma y is just ln of y. So that's how you get the lambda. But in our problem, we're told that lambda equals 5. And so here there's a typo. This should say lambda, which is ln of y, is equal to the number 5. If we solve that equation for y, we get that y has to be e to the 5th. So P has to be the point that has x-coordinate 3 and y-coordinate e to the 5th. Question B. Find the coordinate of point P on the type 2 line that has center C and radius square root of 3, that has the coordinate lambda equals ln of 5 in the standard ruler. So in question A, we just had the coordinate should be the number 5. But in question B, our coordinate is lambda equals ln of 5. Well, the standard ruler for the type 2 line is this messy formula. F of xy is this thing. The good thing is we know the value of c, it's that number 2, and we know the value of r, it's that number square root of 3. So we can put those things into this formula, and we get this formula for the ruler. Ln of x minus 2 plus square root of 3 over y. And that's how we get the value of lambda. But in our problem, we're given that lambda is ln of 5. So we get an equation that says all that stuff equals ln of 5. Now I discuss in detail how to solve this. We solve that equation for x in terms of y. There's a typo here. And we get this new equation. That's equation that we got from considering the coordinates. So I call that the coordinate equation. But we also know that P lies on this line, this non-vertical, or this type 2 line. So we know that P has to satisfy this circle equation. So we have these two equations, the circle equation and the coordinate equation, that have to both be true. We can solve these equations. Now I describe that in these notes. I won't describe it in the video. You can just read the notes. And the result is when you solve these equations, you end up with this. Point P has these crazy coordinates, 26 plus 12 square root of 3 over 13, comma, 5 square root of 3 over 13. That's roughly these decimals. It's quite a bit of arithmetic, and it's interesting, actually. There's some things, special nuances you have to think about. Now, you can also get this from Wolfram alpha. You can tell Wolfram to solve these two equations. You say solve that and that. It's actually that simple. So you tell Wolfram to solve that equation and that equation. You just type all that stuff in on one line, and Wolfram gives you this result. Now we can check our result by substituting that result, that ordered pair, that's the coordinates of point P. We can substitute that into the ruler function. The ruler function is this, remember, and it says, well, what do we get? If we do the coordinate of P, we get 1.609, roughly. By comparison, the thing that we're supposed to get, that is the given coordinate that started this all, was ln of 5. That's roughly 1.609. So the point that we found, this is our point P, is the correct point. Well, that's the end of that example, and that's the end of the video. Thank you.